Doctoral Fellow in Joining and Additive Manufacturing Laboratory at the Metallurgical and Materials Engineering Department at IIT Madras. He is actively involved in innovative and quality research in the field of material science and developing a new class of efficient materials through advanced techniques such as additive manufacturing. He did PhD from Academy of Scientific and Innovative Research, Ghaziabad, India, in association with CSIR Advanced Materials and Process Research Institute, Bhopal. He has worked as a visiting researcher at various organizations including IIT Bombay, NML Jamshedpur, Renisha Pune, and RRCAT Indore. He has published high quality research papers in the reputed journals. Apart from his research career, he has been supporting M-Cube 3D as a technical advisor from the last 3 years. His research interest is additive manufacturing of functionally graded materials, structure, property, correlation of additively manufactured novel alloys and composites, hot deformation of aluminum alloys, deformation behavior of additively manufactured micro lattice and oxidic structures. With this, I am welcoming to your session, sir. Thank you, sir. Now I am handovering session to you, sir. Thank you very much, sir.
Okay, so my voice is clear to everyone. Can you please confirm?
Yes, sir. It is very clear, sir.
And my screen, I hope it is visible to everyone. Okay.
No, sir. I think so, PPT is not visible. Sir.
PPT is not visible?
Yes. No. Screen is visible, sir. PPT has to start. Sir.
Okay, I have already.
Yes, sir. Yes, sir. Now it is visible, sir.
Okay. Okay, fine.
Nice.
Okay.
Yes, sir.
Fine. So, can we start?
Yeah. Yes, sir. Yes, sir. Sure, sir.
Okay. Okay. So, first of all, I would say thank you, Dr. Pradeep and Dr. Ujjwal and other organizing committee members for giving me this opportunity to present my research work and share my research work with you guys. So, I think this is the last talk. So before that, I mean, most of the people have already introduced what is additive manufacturing, what kind of processes are there. And somebody was asking one question about the lattice structure. So I would like to add one answer that MS Lattice is the dedicated software. So if they are hearing, they can note down and they can explore. Another one is Rhinoceros Grasshopper. So they are also based on the equation. You can design the lattice structure according to your need. Okay, so let me come back to the topic. So today I will discuss about the additive manufacturing of functionally gated materials. So everybody knows that additive manufacturing is growing rapidly, and most of the industries are interested to at least replace some small scale components which are really complex and which are difficult to manufacture with the conventional processes. At least those parts as of now can be replaced. So in my talk, one case study also I will discuss in the last, but before that I will just introduce you about the functionally gated materials and how functionally gated materials. So my whole work is related to the metal additive manufacturing, metallic materials. Okay, so functionally gated materials is not a, not a very new concept. It's already there, and in nature, most of the things if you see, those are actually functionally graded. For example, teeth and human bone, and this is some like bamboo tree cross section, and cross section of a dinosaur bone. So the fundamental concept of functionally gated material or utilizing this kind of material is that we can change the properties especially. So there will be, if you need, let's say, thermal properties at one place with moderate mechanical properties, but at another place you need very good mechanical properties and lesser like thermal properties. So like that, we can tailor our material according to our need. So it's able to withstand the asymmetric loading conditions and Most of the cases, if we talk about the turbine blades, there are huge. I mean, it goes around 1600 or 1700 degrees centigrade. It's exposed to the burning gases. So in this material, you also need, I mean, you need the mechanical properties. At the same time, you need some thermal protection on that material. So inside, there is a most of the time people, I mean, Inconel is very famous for turbine blade, and outer region we can I mean add the some kind of thermal barrier coating. So that is usually people use yttria stabilized zirconia, which is very famous for thermal barrier coating. So the thing is how we can achieve the functional gradation in case of additive manufacturing process. So that is a very I mean interesting as well as challenging for the research community. So there are three type of gradation we can achieve. The first one is the porosity gradation, and second one is microstructure gradation, and third one is composition gradation. So one by one I would like to discuss in detail about these. So these are actually this whole uh, results which you are seeing. It's our work. So we are working on all these three type of gradation. So in the first case, if you see, this is actually in this direction, the porosity is increasing. So there are two type of porosity we can introduce. One is the design porosity. So in our CAD model, as a micro lattice structure or any kind of design, we can modify, and we can even closed cell structure, closed cell porous structure, or open cell porous structure, or partially closed or open. This kind of structure we can make with the help of CAD softwares, and then we can print it. But if you talk about the powder bed fusion process, if you will print the closed cell structure, obviously the powder will get entrapped inside those pores. So obviously this laser powder fusion will not be feasible in that case. So that is also challenging. But another one is that there are three type of porosity. One is lack of fusion, another one is metallurgical porosity, and third one is the I mean at high energy density there will be keyhole pores. So if we change our parameters uh, according to porosity variation, we can achieve the porosity gradation. So that is the first case. Okay. Another one is without changing the material, we can achieve different kind of microstructure in single material by just varying the parameters. So these samples, like this first sample you are seeing here, this is printed on the SLM solution machine, and this one is printed on the Intech iFusion SF1 at IIT Madras, and these samples are actually the compositionally graded uh, samples, which again printed at IIT Madras. So here from the center to the outer region, the porosity is increasing because the parameters, these concentric discs are printed, those are different, and since the parameters are different, their the fraction of porosity is different. So that's how we can achieve, and even this particular idea can be extended to the bigger scale, specifically if we talk about the bone implants. I would not say that you can straightforward use it, because for sensor, any kind of bone implant, and it needs a lot of processing. Just it is not very easy task to just print the bone implant and fix it somewhere in the body. It takes a lot of biological investigation as well. But the idea is that we can, if we need some kind of functionally graded bone structures, so this approach can be utilized, I would say. So, and a lot of people are working in that direction. So apart from achieving porosity gradation with the help of I mean the parameter variation, apart from that, the designing lattice structure or filling the bone with the lattice structure and varying the porosity, that can also be one very nice option for bone implant designer. And these samples, actually some cases we need to have we need to engineer the microstructure. So this particular sample has 25 elements within it, and each element is printed at the different laser process parameters. So this is LPBF process part, and that's how we can actually play with the microstructure. So at one place, if you need eqx kind of grain structure, then you can adjust the parameter according to your need. And if we go to the higher energy density side, obviously you will get the long columnar grains, and it will be textured. And the third case, actually, we have printed the functionally graded yttria stabilized zirconia reinforced inconal 718 composite. So from this direction to that direction, the yttria YSZ percentage is increasing, and that's what we have confirmed with the EPMA. So this is basically the electron probe microanalysis result. Okay. So I would like to mention one problem here, which is actually people are facing, that how you are going to make these kind of materials with the additive manufacturing. So in our upcoming slide, I will also discuss about the system development. So there are few researchers which have already developed some dedicated system for the functional gradation. So I'll come to that later on in this presentation. So before that, everybody, I hope everybody is aware about this process. So just one thing I would like to mention, I mean, most of the people are maybe not aware about that process. Apart from these processes, there is another process called electrochemical additive manufacturing. So additive manufacturing is nothing but the layer by layer guided deposition of the materials to make 3D part. Okay. So as of now, there are 7 fundamental AM processes, and they are categorized based on the amount of energy required for the fusion of the material. But another one is that electrochemical additive manufacturing. It's a very new process, and very few people are aware. At least very few groups are working in that direction. It's basically the electroplating process, but in case of electroplating, it's not guided material deposition. But in case of electrochemical additive manufacturing, this electroplating process is basically guided in such a way that we can create a 2D kind of any kind of design. If you give based on the CAD file, it can deposit the material, and maybe in 3 dimension we can also deposit. But this process is quite slow. It's a very slow process. Okay. So one group at CSIR MP Bhopal, Dr. Surender and Dr. N. Satish. So Dr. N. Satish is my PhD supervisor. So actually he was working on that when I was doing PhD there. They started this particular work, and right now it is taking shape, and we are able to print a few bigger structures with that particular technique. But I would say just why I'm emphasizing these things, because I mean, we should be thoughtful that it's not like these are the processes, and we should not think beyond these processes. So that's why I'm emphasizing this particular process, because if you think like in any way we can guidedly deposit the material, it can be added here in the list. So you can be I mean, kind of inventor to new process, and it will be like I mean, any kind of a specific application we can target with the help of that process. Let's say like kind of using magnetic source or other kind of innovative think. You can think in that direction, and we can develop a new additive manufacturing process. Okay. So apart from this, I would like to mention one ice 3D printing process also. I think one group in IIT Bombay, they are working on the cryogenic printing, manufacturing. So that is also a kind of new type of AM processes. Laser powder fusion, everybody know, already aware about this process, so I would not go into the detail. I will just come back like how we can utilize this particular process to develop such I mean, that is such I mean, innovative microstructure or engineered microstructure. So this is basically the functionally graded inconal 718, and this is not actually straightforward. We cannot say they're functionally graded, but it is actually engineered microstructure with the help of element based approach. So let's say you have a part, and that part is experiencing different kind of loading at different location. So this element-based approach can help to develop a kind of microstructure based on your requirements. So as in my previous slides, I already mentioned about this sample. So just I would like to briefly explain like how we have printed. So we make one matrix containing 5 values of laser power and scanning speed, and then based on this combination we are able to calculate the laser energy density. And in this direction LED is actually almost constant, and in this direction, in this diagonal, the laser energy density is increasing. So uh, so Dr. Pradeep, if there is any interruption from my side, you please just call or just stop me there. I hope everything is going well. Just can you please just confirm it? Hello. Anyone please confirm that everything is going well?
Yes, sir. Hello, sir. I can hear you.
Okay. Yeah. So my voice and everything is going well?
Yes, sir. Yes, sir. Yes, sir. It's audible.
Okay. Okay. Fine. So yeah. So I was discussing about this kind of like microstructure you can make in this way, and then pole figure. Based on the pole figure, we can identify that how much your grain structure is textured or not textured. So uh, who is aware about the this texture and all those things, they might understand why we need a textured material and when it needed and when it happened. Basically, after processing, if you perform rolling or any kind of hot deformation or cold deformation process, your material can get textured. Okay. So there are other ways, and with the help of additive manufacturing, you can build the textured material or you can engineer the microstructure. So anybody is interested in this work, we can maybe later on discuss more about it. And the next one is the functionally graded material based on the composition. Varying the composition of what you said. So here I would like to mention in this slide, there is no material change, but the precipitation in Inconel 718, basically gamma prime and gamma double prime is there. So the fraction of this gamma prime and gamma double prime can be can vary, and in most of the cases as printed condition, I think there is a very less probability to form gamma prime or gamma double prime there. But if the laser energy density will be high, the precipitation time will be there, and it will get sufficient time to precipitate, and then this gamma prime and gamma double prime fraction can also increases. Anyways, so just come back to this work. So why this work I'm planning to do, why it's still going on, lot of investigation, and I'm trying to extend this work at the we had tried with the powder bed fusion process. A few people have done this kind of work with the directed energy deposition. Obviously, directed energy deposition is a very much suitable process for the, I can say, the functionally material, because you have a lot of freedom to supply the material there in powder form or in the wire form. Okay, but we had tried with the powder bed fusion, because in case of powder bed fusion, the melting happen in very small region. If you talk about the melt pool size in case of LPBF process, it's around, I would say, 100 micron or 150 micron. In that is in the range, you can get the melt pool size. So there the problem of agglomeration is always there. But here we can avoid these kind of problems, and a lot of, because everything is in moving condition. So some bounce back phenomena can happen, and your reinforcement should not. It could not properly distributed inside the matrix material. So these kind of problems are associated with the LDAD process. So that's why not we should choose LPBF, and we should try some innovative work with the LPBF. Still, there is in India no commercial machine is available for the LPBF, for the functionally graded material development using LPBF. Um, there's one group in China in collaboration with the NTU Singapore. They are working on it and they have already developed one system. But in that case, I think, as I can remember, you can achieve only functional gradation in one direction, either horizontal or vertical. So that is also a very challenging task. So I will discuss more about those things later on. But the problem statement here is when we use any kind of high temperature material, let's say Inconel 718. So we need a bond coat. There is a TGO also there, thermally grown oxide, and this bond coat is there. So the purpose of this bond coat is to avoid the thermal mismatch between the Inconel 718 and this thermal barrier coating, ETS by zirconia. So what we can do, we can replace this whole system with the functionally graded YSZ in Conal 718, because in that case the thermal mismatch will be lowest. Here is still, if you use this particular combination for longer time, there is a possibility every time it is expanding and shrinking. So in that case, this TBC can be broke down, and your inside material, which is separated, then that can got affected during application, and that's how the failure of the blade, or the probably, I mean, people don't use Inconel 718 for blades. I think it's used for the other parts in aerospace, or the gas turbine engines. So okay, so let's come to this idea that we can replace this whole system with the functionally graded material. We can take here in Inconel 718, we can take other Inconel series 625 or anything. We can try, maybe future it is open to all, and thin TBC of YSZ. So once you will get the functionally graded YSZ, there only thin TBC will be required, and there are chances that obviously after a long time duration of application there might be cracking, but here the chances will be lesser, okay, because the coating is thin. In general, the coating size, I mean the thickness of coating is around 1000 micron or 1 mm, we can say, if we are targeting a larger thickness coating, but usually it can be 500 micron or 600 micron in that case. So the question is how we can achieve functional gradation in existing LPBF system. Although I would say this is not the standard method to make LPBF, make this functionally graded material, because we have to mix the powder separately, and then in the dispenser we have to fill different batches of the powder manually, and then we have to, I mean, spread it on the build platform, and that's how we can achieve this kind of functional gradation. But obviously we need a dedicated machine for it to make this kind of material easily. We need not do this whole things manually. So that's why there is a requirement, and some companies, I mean few companies in one is SONT 3D. They have already developed one recorder, and they have patented it for the multi-material development, and they have also printed, I mean, several structure combined with SS316 and copper. So they got, I mean, successful results there. Um, and as I mentioned, one China group is also working in that direction to develop a dedicated system for the functionally graded material. But there are restrictions, so we'll discuss about it later. Before that, I would like to share some results about this particular material. So here you can see this is Inconel 7-minute gas atomized powder, and after coating of yttria stabilized zirconia, basically yttria stabilized zirconia during ball milling, it got coated on the surface of the powder. The thing is, it's again not very straightforward that you can just mix the powder and the functionally graded material you can easily print. It needs lots of investigation. We are also working in that direction. Let's say if you are changing your composition in LPBF, you have to change the parameters. Okay, so if you are if you want to achieve the the functional gradation, okay, there will be more than thousands of composition will be there from bottom to top if you are varying the YSZ or any kind of functionally graded material you want to develop. So for each and every combination of those composition, you need a separate parameter. That is a very challenging task to like how we can assign those parameters. So we are working on this particular problem as well, and I'm open if anybody wants to collaborate in that in this problem, and that's actually it needs some kind of thermocal studies we need by mixing 2 or 3 materials. I'm very new to it, and I'm trying to explore some of the things there. So apart from the other theoretical calculations, some experimental studies can give better results. Let's say if you see this differential scanning calorimetry, uh, we got I mean partial we saw that partial liquefaction is happening once we have added the ETH by zirconia. It means that ETH zirconia, which is coated on this particular inconation unit powder particle, it's affecting the liquefaction process during melting, and that's why to melt it properly we need high amount of energy. So that's what this kind of result we got here. So these you can see these ABC3 images. So the first one is printed at the constant laser power, another one is printed at the increasing stepwise increment in the laser power, and third one is 20-watt step increment in the laser power, and that's how we are able to achieve lesser cracks during printing at the 4 weight percent YSD region. Okay, so some SCM the main findings of this particular work is that after the addition of ETH by zirconia, the thermal expansion, like coefficient of thermal expansion, is slowly it's decreasing after the addition of ETH by zirconia. So we have tested this material with the dilatometer, and we uh, the results which suggest that after addition of ETH by zirconia or the functionally graded by acid in unit, it can really accommodate the the thermal mismatch. Okay, so we can target this material, and maybe in future uh, we can we can plan this material to use somewhere in the gas turbine engine. The problem with this technique right now, the problem is that we cannot target the complicated shape. As you see, when we have printed these samples, we have filled these patches, and it's quite simple. Like this is a simple experiment. So we have not planned any kind of component here, but maybe in future this might be challenging until and unless we don't develop a dedicated system for it. Okay, so some of the other materials related research, I think I have less time, so I will not go into the detail of these TM and EBST results. But the thing is, I just wanted to express that how when we are adding ETH like zirconia, then it's actually the grains are EQX now after the addition of ETH by zirconia. That also we need to explore more. And this is the TM results. So TM Laves phases are there, and the gamma phases are there. So that is indexed with the SAD pattern. So graded porosity case, the second one, which is like I mentioned already in the initial slides, that there are 3 types of pores. So lack of fusion pores, if you have less amount of energy density, and then it's once you increase, there will be obviously there will be evaporation pressure will be developed above the melt pool, and that can result in the keyhole porosity, and that's it's actually the keyhole porosity. In general, the shape of keyhole porosity is spherical. So that can be useful in one sense, but obviously you are increasing the energy density, you are spending a lot of energy there. That will be costly if you want to make any kind of consolidated porosity. But let's we can, for dedicated application, we can target this, no problem with that. And So I hope you understood like how we have achieved this kind of consolidation in porosity. Why I'm targeting this particular thing, because in LPBF, if you want to make closed cell posts, it's impossible, because during closed cell printing, if let's say we are printing a sphere, okay, closed sphere. So once you print it, this whole powder will get entrapped inside that sphere. That is the problem. So to avoid that problem, I mean, we can utilize this spherical pores or keyhole pores as a porosity, and we can functionally graded kind of porosity we can achieve. So again, it will be some kind of parametric investigation you need to do, and you have to identify like at what energy density combination you need, what amount of like how much porosity you are achieving, and that's how you can play with the parameters, and you can plan your experiment according to your need. So these particular things also can be extended. So you can see these are the concentric discs. Each disc is printed at the different parameters which have been selected with this process parameter window. So that is also a very novel experiment, and I hope I think, I mean, very few people have performed this kind of experiment till now, and maybe in future we can target I mean the extended version of it. Okay, so some of the results are here. Anybody want to discuss more about this work? Maybe later on we can catch up. So that again, the problem again and again I was mentioning that how you are going to enable the laser powder bed fusion process for the consolidated materials. Okay, so there are currently there are two type of powder supply systems are there in the market. One is gravity based supply. So Renisa is using this kind of system, and I think in other machines like I think EOS also have similar kind of things. I'm not sure, but Renisa they have this gravity based powder supply system, and the dispenser based supply. So this iFusion SF1 Intech, uh, sorry, yeah. So US actually have this dispenser based supply. Okay, so Intech actually, I mean, they have collaborated with DMG Mori, and they have developed a very nice system. And I was in charge for that system in IIT Madras, and I have used it extensively for larger components as well as the small scale components, innovative material design. So I found that that system is quite good. Um, so these two kind of supply systems are already there, but whether this supply system, powder supply system, are going to solve this problem for the development of like consolidated materials, no. So that's why we need some kind of innovation here, some kind of thought process needed to do that. And still I'm saying, I mean, it's a very challenging even to develop this normal powder supply system. It's actually in tech, I saw that, I mean, they're very hardworking, and to getting that level is itself a challenging task. Okay, but maybe in future you can think in that direction. We can expect some updation on the LPBF system from Intech. So this multi-material LPBF ultimately, so this kind of material switch option, which is again available in the S180 3D, they are collaborating with the uh, one company. They have already patented this powder supply system. Okay, so this graded transition. So our target is to achieve this graded transition. So to solve this problem, we have uh, printed with the help of FDM. We have printed one prototype. So this whole work is performed by my students, and they have actually designed this particular. I mean, kind of CAD file they have first developed. And here I would like to just share a few important thing of this work, and we are actually writing one project on this particular thing. So I would request everyone to please not take pictures, or it's okay. I mean, I'm okay with that. The thing is here, the innovative part is that if we fill this chamber with different composition, and we rotate it at particular angle, we are able to achieve the different composition on the build platform. And that's how, when we stack these layers, in 3 dimension, we are able to achieve this kind of gradation. And with this particular approach, we can target this 1-dimensional gradient as well as the 2-dimensional gradient. And the third problem, which is 3-dimensional gradient, is still open for everyone. If anyone have idea, they can discuss with me. I'm open to it. And just try to think in that direction, like how we can achieve the 3-dimensional gradation in LPBF during the powder supply. Hopefully this SONT can solve this problem in the future, and they might have developed, but still, I mean, it's restricted to the material and this graded region. The main problem is that this graded region, what kind of process parameters you you have to find out. Okay, so it is not very easy task to just take multiple materials and try to print it in the functionally way. It, apart from this system development, it needs a lot of metallurgical investigation to make these kind of functionally material. So it should have some kind of like metallurgical compatibility. Let's say if you are mixing one material into another, the fraction of, let's say, iron is increasing, and it is resulting any deteriorating phase in the other material. Obviously you will end up with cracks and very like poor properties. So again, it's a very challenging task, and it need a lot of investigation before printing, or before we say that yeah, this is the material I can print. So you cannot straightforward, you cannot say that. Before that, you have to provide a lot of documentation on the material aspect. Okay, so this work I would like to just share. So that actually, this problem comes under the category of design for additive manufacturing. So this is printed forging punch. So this is copyrighted by Center for Futuristic Mobility, IIT Madras. So with Professor Murgian and Dr. Basil was there involved in this work at IIT Madras. So the Super Auto Forge, I hope everybody know what they do. So they're a forging company for steels and aluminum. So they use this particular punch for the forging operation, but after hours of application, it got heated, and once it got heated, this property of this particular material got degraded. But if we are able to introduce some kind of internal channels there, we can supply some kind of coolants there, and then we can maintain the temperature at, like we can fix it to some value, and it will, obviously it will not I mean, some kind of hot deformation, and these things can be avoided. So that's all. I would like to acknowledge Department of Science and Technology for the Inspire Faculty Program. So I'm currently working in PDPM Triple ITDM Jabalpur as a Inspire Faculty in Mechanical Engineering Department. So if you interested to collaborate, or you have any idea, that I already shared a lot of things in my slides. If you want to extend those works to next level, you can catch up anytime. I'm open to it. I would like to acknowledge the Joining and Additive Manufacturing Laboratory, IIT Madras, and this SAF. So a lot of other things like characterization and other things we do with them, and Microstructural Mechanics and Microforming Laboratory, IIT Bombay, and this Advanced Material Processes Research Institute, and MCube 3D. So this company we started during PhD, and we are working on it. We are trying to get some AM market in central part of India, and maybe we can extend it to the next level. And some kind of collaboration we are still doing with Intech, IIT Madras, and Bombay. So anybody want to ask any question? I'm open to it. I hope you'll be able to answer. You can unmute yourself and you can ask the questions if there are any. Thank you so much for being patient.
Thank you very much, sir. Participants, any queries you can ask. I think Durgesh Sharma raised a question. Please proceed.
Okay, you can unmute and ask if any questions is there. Otherwise,
Yeah. Hello, sir. Can you hear me?
yeah, I can hear you. Yes.
Yes, sir. Thank you, sir, for your talk. Just have two questions. Can you move
Yeah.
to slide number 18, sir?
This one.
Yes. Sir, in this slide, I'm looking into this FE simulation and influence of design variables. Can you give some insights into this block, sir?
Okay, design variables is basically see this punch is in experiencing the loads also. So our design should be such that it should not affect its mechanical property. It should able to wear the I mean it should be able to wear these loads which have been applied on this punch. So when we are planning to introduce some conformal cooling channels inside it, we can play with the diameter. What should be the diameter of these things? So and whether it should be vertical in this way or it will be spiral or any other kind of approach we can do. So those are basically the design variables, and with the FE simulations, the simulation part was performed by Dr. Bashil. The sprinting and designing part was taken care by me. So but still, I mean, this with the help of FE simulation, we can identify that what kind of loading after introducing these channels, what kind of loading it is experiencing, and whether we should remove the material or we should add the material. Like that, we can. Yeah, I hope.
Is this work got published?
No, it's actually not published. It's a company work, so we don't have even the data for their testing, but they have tested it. Um, Maybe actually the companies, they are not very much interested in publications. They just want to solve their problem, and if it is like useful. And then once I came back here in Triple ITDM Jabalpur, otherwise we could publish this work, but still it's under process and it's going on.
Okay, sir. And my second question is related to element-based additive manufacturing. Can you go to the that slide? Maybe it's slide number 3 or 4. I don't remember.
This one,
Slide number 6.
element.
Slide
Number 6. Yes. This is element based approach.
Yeah.
You are able to see it?
Yes, sir. Yes. So in this, my question is like, for suppose I'm assuming this element 1 to 25 is a space where we have to deposit material in that space, which consists of 25 blocks.
Yeah.
Let us assume I have multi-material of two types, and if I want to deposit these two types of materials in different locations, not evenly spaced, I mean like not uniformly spaced. Maybe some 10 blocks have one material and another 15 blocks have other material, which are spaced in a different pattern.
Yeah,
So will it be possible?
Yeah, it will be possible. Definitely, if we have a multi-material system, like if you are able to spread the multi-metal powder on the build platform, you can achieve. There is no problem, and even you can play with the parameters as well. So I think obviously if you have that kind of setup, but still in India, I think in my knowledge, I think we don't have any machine which is having like multi-material printing. There are few companies that they are working in that direction, and maybe soon we will have it somewhere.
Will it be possible even this non-uniform pattern through thickness also?
Non-uniform pattern.
For suppose,
I'm not able to understand your question.
for suppose this is a plane. This is a 2D surface which consists
Yeah,
of
2D surface.
25
Okay.
elements, and
Yes.
means like in z direction or
Yeah, I understood your point.
into the
Actually,
into
in
the
three
plane.
dimension, how can we achieve the different, element like that you are asking, I think.
Yes. In non
So
maybe
yeah, obviously in three
non-uniform.
dimension, yeah, non-uniform as well as any kind of random. Uh, as I said, this work is the engineering microstructure. So you want to engineer the microstructure according to your need. If you
Yes.
extend this particular work at component level, maybe on the surface you need equ grains, but at the inner side you need the textured grains or these long columnar grains. So that kind of need you may have in your part. So that's how in three dimension we can think of, we have to first create this kind of matrix, and this matrix we can create for each layer separately. So, so let's say you want to print it 300 layers. This kind of 300 matrix we can stack one upon one, and then for let's say we target 1 mm or 2 mm thickness. So after 2 mm thickness, the parameters, whole parameters will change. So like that in three dimension we can stack, and we can plan in that way. So the voxel approach, voxel or say element based approach, it can be applied in three dimension as well. There's not a problem, but I have not tried it. So I mean, we can think
Uh,
of no
then
problem.
we have to write a code for slicing also, I think so.
Yeah, yeah,
The
definitely.
slicing can't.
And
It will assume a
it will be
uniform
tedious.
layer
So
property.
yeah, so it's a very interesting point you have made here. Actually, I was thinking, see, once we will have this machine for the development of engineered microstructure, maybe we can introduce one module, one software module into the existing software which they proprietary software they give with the machine. In that software, we can add one module for the element based approach. So it's obviously it can create some business as well. I mean, so you made a very right point. Yeah. So anything else you want to ask?
Yeah, this is actually I'm working on topology of structures where my structures looks kind of these patterns. Maybe in
Okay.
future there is a possibility and high demand in aerospace or space kind of applications where they want to they want to design these engineered structures.
Yeah.
Kind of a multi.
Definitely. Yes. Mhm.
Yeah, thank you for your.
Okay. Okay.
Any other queries from participants? If it is not, we'll close this session and we'll forward to go for validatory function.
Oh. So thank you so much, Dr. Pradeep and Dr. Ujjwal, for inviting me. So anybody is interested to collaborate, they can directly contact me on my email. I will just type it in the chat box. And
Sir, good evening, sir. This is Shivaraju, sir.
yeah,
Sir, you are suggested few number of lattice design softwares. Can you please kindly repeat
yes,
once
yes.
again?
It's actually one open source software is MS Lattice,
Yes,
and
lattice.
MS Lattice you can design the functionally graded lattice structure there, uh, uh, the gyroid structure, and other kind of minimal surfaces, lattice structure, P surface, or other kind of lattice structure you can design there.
Sir.
And another software is Rhinoceros Grasshopper. So Rhinoceros is the software name. It is having one Grasshopper module on which you can perform the dynamic designing. So let's say you want to convert one equation into 3D. You want to make it kind of a lattice structure. So gyroid structure is nothing but one equation,
Sir.
sin x cos y plus cos x sin z, and this kind of equation is there for gyroid structure. If you go and check, you'll find it. So if you want to develop that kind of lattice structure, you can just use the grasshopper module. And rhinoceros is free for 90 days. Otherwise, it is also very cheaper. The cost is, I think it will be less than 50,000 for single user. Yeah.
Thank you, sir. Thank you so much, sir.
Okay. Thank you.
Thank you, participants. Sir, thank you very much, sir. Your lecture is very much useful for everyone to enrich their knowledge in all the ways who is working in this particular topic. Thank you very
Yes,
much,
my
sir.
pleasure.
Jitendra, sir. Sir, can you stay for some balance? Okay, sir.
Yeah.
Yeah, okay, sir. So I request participants just wait for 2 minutes. We will start the validatory function. I request don't leave anyone from the meeting. Good evening, dear participants. So I think now it is we came for concluding the session. It is not the end of the session. I am thinking it is the starting of the era of the additive manufacturing who is working. Maybe we'll maybe we'll conduct more FDPs in this particular area. So all the participants with this all these 5 days attended in your busy schedule, and I think all the people got good knowledge in the AM. So we seen all the areas about AM materials and about structures. So in all aspects we covered in from all resource persons from IITs and IITs and industry persons. So now I request Dr. P.H. Varaprasad sir to host the session for a validatory function. Thank you, sir.
Thank you very much, Dr. Pradeep Garu. So, good afternoon, one and all. I welcome Dr. Pretam Kumar Das, HOD, Mechanical Engineering Department, Aditya Engineering College, Sorampalem. I welcome Dr. Ujjwal Kiran, is the coordinator of this program, as well as I request Dr. G.K. Pradeep Garu. He is also one of the coordinators for this program. And I welcome today's research person, Dr. Jitendra Kumar Tiwari Garu. So he is the faculty IIIT DM Level 4. So it is my proud privilege to have a small participation in this program. Now I request Dr. Pretam Kumar Das, HOD, Mechanical Engineering Department of Aditya Engineering College Autonomous, to say a few words about this program.
Yeah. Thank you, Dr. P.H. Varaprasad Garu. Respected resource persons, attendees of the FDP, and conveners and organizers of the FDP. A very warm evening to all of you. I would like to extend my heartfelt gratitude to all the resource persons who have accepted our invitations and given their valuable times to us and enlightened to all of us in different research area. And these 5 days, the FDP what we have organized, the future scope for additive manufacturing in industry and biomedical applications. I hope all the participants have gathered much knowledge about the materials and the applications in area of biomedicals. So in this aspect, I would also like to thank all the participants for their enthusiastic participation. And you very well know that without you all participants, the event won't have been possible in a successful mode. So thank you everyone once again. When we plan for an event, it is not possible to complete an event within a overnight, and any kind of event, if you plan or we are planning the department, it requires a month to make it successful or to make it happen. So for this event, I definitely, from a bottom of the heart, I want to thanks the convener of the program, Dr. Ujjwal Kiran, the organizer of the program, Dr. B.H. Baraprasad, Professor of the Mechanical Department, and Dr. G.B.K. Pradeep, Assistant Professor in the Department of Mechanical Engineering. Thank you once again to all for your continued support to make this event successful. And the special thanks to Dr. Jitendra Kumar Tiwari and all the resource persons who have accepted our invitation. Thank you once again to all, and thank you all the participants. Thank you all.
Now, it is my privilege to say a brief report on this 5-day program, that is Future Scores for Additive Manufacturing in Industrial and Biomedical Applications. Now, first thing, I want to acknowledge the resource persons. So on 17th July, a resource person started this program, that is Dr. S. Anand Kumar, Assistant Professor, Department of Mechanical Engineering, IIT, Jammu. He explained about the aspects of design for additive manufacturing. And later in session 2, that is first day, the research person is Dr. Mallikarjuna, Assistant Professor, Department of Production Engineering, NIT, Tiruchirappalli. And his topic is computational modeling of DED process for deposition of titanium aluminide for aero applications. And later we went to second day. So that is the resource person, Dr. M. Duraiselvam, Professor, Department of Production Engineering, NIT, Tiruchirappalli. His topic is advances in additive manufacturing. And in the second day, second session is completed by M. Nagesh. His topic is applications of metal additive manufacturing in defense applications. He is working as a scientist, Gas Turbine Research Establishment, GTRE, DRDO, Bangalore. And on the third day, research person by Raghukumar Garu explained about solving complex biomedical case studies using additive manufacturing. Also, he explained about the almost all case studies he handled. And he is working as a professor, Department of Mechanical Engineering, NIT Warangal. And next session is Dr. Gino. He explained about the laser-directed energy deposition, fundamental issues, and research case studies. He is the Assistant Professor, Department of Mechanical Engineering, Teesside University, United Kingdom. And later, that is yesterday, session started by Dr. K. Gopal Krishna, Senior Principal Scientist, CSIR, National Metallurgical Laboratory, NML, Jamshedpur. His topic is metal additive manufacturing, opportunities and challenges. And yesterday, second session is Jitendra Kumar Chaurasia, a specialist metal 3D printing, M2 Nest Solutions Private Limited, Bangalore. His topic is challenges in widespreading of laser-directed energy deposition process in Indian market. And today's first session is started by Mr. Rakesh, Technical Officer, National Center for Additive Manufacturing, Hyderabad. And his topic is materials in 3D printing. And now the resource person, all of you know, So Dr. Jitendra Kumar Tiwari, TST Inspire Faculty, IIIT, TF Jabalpur. His topic is additive manufacturing of functionally graded materials. So why I am acknowledging all these people? So they made this event very successful. So the success is the measure of the participants only. So now there are 511 registered, and in our WhatsApp group there are 341 participants, and the daily attendance almost all approximately 200 per day. So which gives the boosting to us to start to plan some more events like this in the future. So therefore, I request all the participants to extend their helping hand or participation in this programs, that is the FDPs, which are planning to organize in the uh, future. Okay, thank you very much. Now I request any one of you please give feedback of this 5-day program. Any participant, come forward and share your views to improve ourselves. If we give feedback, then only we can improve our quality, and it will be reflected in the next faculty development program. Don't hesitate. Please give any sort of feedback, even that is a negative.
Hello, sir.
Please unmute your mic. Yes, madam. So please, the participant who are giving feedback, please switch on your camera.
Can you hear me, sir?
Yeah, you are audible, madam.
It was indeed a nice program organized by Aditya Engineering College. I have come to know about this program by Dr. Ravi Kumar, sir. And all sessions were beautifully arranged, like all speakers were very knowledgeable. And the coordinator, that is GV Krishna Pradeep, was very keen in updating all the information in the group as well.
Yes.
And
Yes,
all speaker gave very good and informative, sessions on various topics like metal 3D printing, maybe DED, and then materials, future aspects. I wanted to know a little bit about the polymer composite. So I took the number of Mr. Satish Rakesh K today, who had given some insights about the materials of the 3D printing, composites and continuous fibers. I'll definitely contact him. And I think it is going to be benefited to all the participants. We will be taking this knowledge and helping this knowledge will be helpful to us in future. Thank you, Aditya Engineering College, for arranging such a beautiful program. Thank you, sir.
Thank you very much. Thank you very much. One more thing. So will you please switch on your camera?
Yes, sir. Yes.
Okay, madam, and one more thing. Will you please just share your anything we need to improve?
What, sir? Can you please speak louder?
Yeah, anything we need to improve for betterment of this
No,
program?
actually, I think all sessions were started also in time. Otherwise, normally, if we see online lectures, there are glitches in the internet connections or something. One session is
Yes,
over,
ma'am.
and other speaker is already waiting for the session. So
Yes.
I don't think there is a scope of improvement. But you can
Okay.
keep it on the offline mode, so we would be able to take the gist of it in a correct way, proper way, more benefited to the research scholars. So if it would
Definitely,
be
madam.
offline, that is only one suggestion, sir.
Okay, madam. Thank you very much, madam. Thank you
Okay,
for your
thank you, sir.
suggestion. Okay.
Hello, I'm audible.
Yeah, audible, sir. Please go ahead.
Sir, Dr. Vishal Dutt from KB University, Kalburgi. It was a nicely arranged what you call FDP is there. After COVID, again the online platform is gaining importance, and I am also what you call advocating the online platform because it saves the time and it gives convenience for the participants as well as for the resource persons to participate in this one. So all sessions were very good. If these sessions were kept at in 2 sessions, they were back to back. Okay.
Yes.
So if one was in morning, one was in evening, that would have been a better one. This is the one small improvement what I can suggest. So one more is that one in between what you call quiz-like thing, 1 or 2 5 questions or sessions.
Okay.
So that will be also will add it up. So rest, I think rest of the things are very good. There is no other thing, what you call covered nicely. Thank you for the organizers.
Thank you, sir.
To go for one more FDP, contact the
Yes, sir.
or any kind of. Thank you.
Okay, sir. Thank you, sir.
Yeah, good evening, sir.
Good evening, ma'am. Go ahead.
Sir, this session was very nice, sir. From the last 5 days, so much topics you have to cover,
Madam,
sir. So
please,
this much of
madam, excuse me, madam. Will you please
sir.
switch on your camera?
Sir?
Will you please switch on your camera? Yes, madam. You can go on.
Good evening, sir. So I am Sujata from Sriram Engineering College. So from the last 5 days, the total session was very nice, sir. So much topics you are covered. So like this, so many FDPs you are keep going on, sir. Because of very helpful. Why? Because I'm a PhD scholar right now, sir. So I got so much information from the what are the sirs, those doctors told. All these are very helpful for me, sir. Thank you so
very
much,
madam.
Thank you, Aditya College and total management and total who are the back in this total FDP. So thank you so much, sir.
Anybody? Now it is time to vote of thanks. I request Dr. Ujjwal Kiran to propose vote of thanks.
Now is it audible? Okay. So thank you so much, sir, Professor. And now it's came to end vote of thanks on behalf of Aditya Engineering College and behalf of Department of Mechanical Engineering. I am really proud and grateful to express my heartfelt thanks to all who have made this online FDP program successfully. And first and foremost, I would like to thank our chairman, sir, Dr. N. Shesha Reddy Garu, and Vice Chairman, sir, Dr. N. Satish Reddy Garu, for always being supportive. And if you initiate anything, definitely they are always supportive to us. And for both of them, Chairman, sir, and VC, sir, we are really thankful to you. And coming to next, I would like to thank my sincere thanks to our beloved principal, sir, Dr. M. Srinivas Reddy Garu. Always he has been encouraging, and his background is from mechanical only, so he used to encourage us and support us if we are initiating any, and he used to nurture us. And I would like to express my heartfelt thanks to our head of the department, mechanical engineering, Dr. Pritam Kumar Sardas, for always supporting. He is very friendly with us, and if you are initiating, and actually this FDP was planned before, like on last year, November, December time, but as Aditya Engineering College, we went for NAC as well as NBA programs. So we don't have that much time to spend on this. So after completing this, both HOD itself, he told you how to initiate one FDP. So with the idea of Dr. Professor Sir and Pradeep Sir, we three combined and we have initiated this feature scopes for additive manufacturing in industrial and biomedical applications. So I thank HOD Sir for giving all the resources, and he always supported us in every aspects. And I would like to thank and appreciate to our guests who have given their time out bounding, like even though they have busy schedules, whenever we call to them, like arranging the schedule, some speakers having on some other day, but somehow they have managed the timings, and it was well planned because of their given time. So I want to appreciate each and every speakers. And finally, I would like to thank our coordinators, again, Professor B.H. Varaprasad sir, and as well as Dr. Pradeep, because I know Pradeep sir has really, I really appreciate his patience level. So after completing this section, we have to save the video and all these things. And again, we have to create link for next day, and you have to initiate to each and every participant, and you have to interact with them in WhatsApp groups. So in all the way, Dr. Pradeep and Varaprasad sir has taken initiative and hosting the sections, sending the sections. So I really thankful both of them. And finally, I would like to thank all the deans and other department HODs always supporting. And finally, I want to thank our department mechanical engineering staff members who have supported us in everything. They have always back end there giving support to us in conducting this kind of online FDP also. And in conclusion, I want to conclude behalf of Aditya Engineering College. I would like to express my sincere thanks to all of you. Jai Hind, thank you, and section hand on to Varaprasad sir.
Thank you, sir. Now the time for national anthem. Jai Hind.
Thank you, sir.
Thank you all. We'll meet some other day.
Jai Hind.
Thank you all the participants.